Let us begin the seminar. First of all, we have to have an installed Jupyter Notebook on your laptops. There are some guides in the internet, so I will not focus on that specifically. I will assume that you have this piece of software installed and you can just open it in your browser. We will use a library that is called OpenCV. And the following seminar will require some basic knowledge of Python. We will import this library, and if you don't have it installed, you can install it from Jupyter Notebook with the following command. What it will do is that it will omit the exclamation mark and execute this command in the shell. I will not do that because I already have OpenCV installed on my computer. So let's check the installation. If this cell will run properly, that will mean that the OpenCV library is imported. Yep, it's fine. So now let us check the version of the library. It could be done with the following command. Yep, this is the version. You can have a different version of OpenCV, but that's generally fine. So what is this library about? This is a de facto standard in computer vision and in robotics regarding the computer vision. This is the library that is commonly used to process images, videos, to work with the data, to detect objects. It is capable of doing the classical stuff, also some almost classical stuff like Haar cascades and so on, and also it has support and close integration with the neural networks. So the majority of the neural network-based pipelines have some kind of data loading or pre-processing written in OpenCV. So it's very important to be familiar with it. We will start from the images. We have talked about the images, what are they basically, and here I have an image, the same one that we were using during the lecture. It's rather small. The resolution is, well, we will check the resolution, and if I try to zoom it, here you can see the individual pixels. Those are the values that we were talking about, and here you can see this red blob of color, which is the basketball. And if we zoom it out, it will look like a regular normal image again. With this example, I would like to demonstrate that we have to consider all these images precisely as array of values, and that's it. So let's check its properties. It has the size of 263 by 197, and here you can see, although it's in Russian, the color space of this image is RGB. We can do the same thing. We can open this image with the OpenCV library, and we will do that slowly and steadily, going through its properties. The command that is supposed to load an image for us is the following. It's pretty straightforward, and it's called imread. And here in the asterisk, we have to specify the path to our image. Here is the Jupyter Notebook. I will rename it later. And in the same folder, in the folder Khalifa Vision, we have this image basket.png. So I will insert it here. And since this file, this Jupyter Notebook, and the image belong to the same folder, I don't have to specify any path over here. Okay, let's try. It's working. It's fine. Let us try to print what is an image. And before I do that, let's reflect just a bit on the things that we expect to have here. Well, if image is an array, what could we see if we print it? Probably we will see a big matrix that will not fit into the screen, and it will be filled with numbers, with values from 0 to 255. Let's try. Indeed. So here we have a regular notion for printing three-dimensional arrays. This is the triplet that is representing the color of the first pixel in all of them. And this stands for blue, this stands for green, this stands for red. In OpenCV, the convention is that the color space that is used is BGR instead of RGB, but that's the same exact thing, really. So that is not that much important, but we just have to remember that it is so. Let us now try to have access to a certain element of this array. Let's try printing element number 0 by first axis, 15 by second axis, and from red channel. Why not? It's 29. Okay, so that's just a normal image. It's just a normal value, normal integer. Let's check its type. We were talking about the type. Now let us demonstrate that by the code. And here you can see that this element of a three-dimensional array has the size, the type of NumPy, which is the library that is commonly used. You know that for sure if you're familiar with Python. And the type is unsigned integer with 8 bits in the encoding of the value. Unsigned means that we cannot have any negative numbers here. And it indeed makes sense because there is no such thing as negative luminosity. The next thing that we are going to do is we are going to show this image on the screen. The function cv2.imshow has two parameters. First of them is the name of the window that we are going to show, and the second is the frame itself. With imshow, we can visualize two-dimensional arrays like the masks and three-dimensional arrays like normal RGB or just three-channel images. So what will happen if we run this code? It has executed and that's it. What's the deal? Well, the thing is that we have to stop the execution for some time for us to be able to see it, to see the frame. So let us use another function from OpenCV, which is waitKey. And it has as an input the number of the milliseconds that we have to wait for. So if I will pass 5000 here, this window will wait for me for 5 seconds. And after 5 seconds, it will close. No, it didn't. Excuse me. It's the execution of the cell was complete, but the frame is still here. It's just hanging. That's because we have to manually call a function that will close all the frames. So there are some technical things that we have to do, and we will briefly cover them. And we will not focus on them too much. So what is happening here is that we first wait for 5000 milliseconds, then we call a function that will close all the windows, in our case just one window, and then we will wait for another 10 milliseconds for all the signals to properly reach their destination. So, yep, now it worked. And here we can set any timing. It will be measured precisely enough. And if we want this program to wait for us for an indefinite period of time, we can pass here a 0. Another thing about this function that we have to talk about is that it's called not sleep or not wait, but wait key. So it is waiting for a key on a keyboard to be pressed. We will use that later, but for now, we just need to know that if we are calling the function wait key from 10 milliseconds, we expect this function to wait for a key to be pressed for 10 milliseconds. And if we are calling this function with 0 as a value of the parameter, it will wait until any key will be pressed. And the output of this function will be return, basically like this. So we will use that later. For now, let's just use this function as a way to stop the execution until any key is pressed. Okay, let's check. So there's a frame, we can examine it, work with it somehow. And when we want to close it, we can press any key, and we will be done. The next thing that we have to examine about this image is its size. We have already checked the size of this image with the operating system internal programs, or whatever you call it, the default ones, the viewer, the image viewer. And here we can check the shape of this image, even omitting this viewing part. We can check the shape, and what can we expect from this? Some spatial dimension, another spatial dimension, and 3 as the last part, or the size by the last axis. Here you can see the value of the height of this image. It's rectangular for sure, and its height is smaller than its width. So we have to remember once again that in OpenCV the convention is that the first value here is the height of the image. Another slightly confusing thing is that the default order of the channels is BGR, and it could be confusing in the beginning. So let's just keep that in mind. So the second dimension is the width of the image, and the last one is the number of the channels. Now let us try to make this image slightly bigger. Let's resize it. Clearly, that will not get us any new information, but we will be able to see the details slightly better. So let us introduce a new variable. It will be image resized. And I will call a function from OpenCV that is conveniently called resize. In OpenCV, there are functions for almost any occasion regarding the image processing that you could need. So the first parameter will be the image itself, and here we have to pass a tuple, two sizes, two values that we want this image to become. Okay, so I can set, let's say, 1000. Let's try. And then I will uncomment this and pass image resized here. Let's see. Okay, that makes sense. But the thing is that apart from this image being enlarged, it has now new ratio of height to width, which is 1, and it was not like this. So all the objects are elongated along the vertical axis. And that's not cool, because we are losing the proportions. So In order to demonstrate that, more clearly, let's try to calling the same function but with new absurd parameters. It's clearly distorted. So we have to somehow preserve the perspective, we have to preserve the ratio between height and width, the proportions. So we can use the shape that we already obtained. The first thing here is height, the second is width, and the last one is the channel number. So we can just unpack that triplet into these three values. And since we're not that much interested in the number of channels yet, we can ignore that and substitute this with an underscore. Okay, and here we can now use the sizes. It has to be width, let's say times 4. Let's increase the width of the image by 4, and the same goes for height. Yep, so the image is now bigger and the proportions are kept intact. Now let us check the channel-wise division of this image. So let us first extract the blue channel of this image, or the resized image. We will use normal Python slicing, like this. And whatever, I will just substitute this with the only image that I will be showing, so it will be B channel here. Let this not fool you, that is not a grayscale image, it's just the single channel from it. And yeah, maybe it would be better to show them side by side. Hold on. So I will show both the resized image and the blue channel. Okay, so let's take a look at those pictures. The lines that are white here are white or intense in the blue channel as well. That makes sense. Here on the wall, you can see that these blue strips are slightly brighter than the green strips. And this red basketball in the blue channel has very low values. That's why in the blue channel it has a dark color. That makes sense. And now let us check the red channel instead of the blue channel. What can we expect from that? Here the situation is really different. So in the red channel, these blue stripes on the wall are dark. And on the contrary, this red basketball here is brighter than its neighborhood. And yeah, this blue sock here in the red channel is dark. Try pausing the video and try to make sense of the different objects and how are they represented in specific channels. If you follow along with the code and the image, try for yourself to show the green channel as well. Let's do that. Okay, in the green channel, the values on the green field, on the carpet, are high enough, and the value here on the sock is high enough. So that again makes sense. And what about taking some part of the image? What about cropping some part of it? Let's do that. I will take all the channels here, and out of laziness, I will probably not rename the variables, just for demonstration purposes. Do it like this. Okay. Okay, so the thing here is that we can take little slices from the image, and where are the coordinates 100, 100? They are somewhere here, right? So let us first, let's try to find the proper, wait, what? Okay, now let's take a bigger slice. It'll be 350. That's better. That will be more evident. Okay, so this piece of image that was cut from the frame contains all the same pixels and all the same information as this piece of the original image. So we can crop images to a certain size. If we are not interested in half of the image, we can omit it and ignore it completely. And this is the way to cut the image in spatial dimensions, and with changing the last value of slicing, here we can address certain channels, let's say green, red, and blue, and so on. The other thing that we can do is that we can apply some mathematical operations to these images which are arrays. We can, let's say, set all the values in all the channels in this square to be 100. What do you expect from such a piece of code? Let's run it. And here, this rectangle was painted dark gray. That's because we have filled all the values in all three channels in this rectangle by the same value, by 100. And yes, first let me comment that. And what will happen if instead of 100, I will fill them with 200? It has become light gray. So here I can specify any values to any channel, and if I do it, let's say, for blue channel like this, I can specify high enough value, like 240. So here you can see that in this sub-area, in this crop of the picture, the values of the blue are clearly high enough. So in the processing, we're basically using the same instruments. We are accessing certain elements of the arrays and changing their values and comparing them to some other values that we have specified previously. By that I mean that this whole image processing stuff is not that much complicated. It's nothing more than just arrays and accessing them in proper spatial dimensions. Now let us move towards a new thing, which is the reading frames from the web camera of the laptop. Now let us move to the following section, which will be about opening a web camera of your laptop. Probably you have been already curious about that. If we are able to open an image and do something to it, can we also open a web camera as an input for our frames? We can do that, and I will use a separate slide, a separate cell in Jupyter Notebook. And the key difference here will be that we are going to read the images from the web camera in a loop. Here we were just processing one single image that we have read from the disk, and here we have an infinite, virtually infinite stream of frames coming from the web camera. So let us first instantiate the camera object. I will do it using the function cv2.videoCapture, and 0 here is the number of the camera in the system. If I will plug an extra camera here, separate USB camera, I will have 2 cameras in the system, and I will be able to access them by 0 and 1. And by now I have only one camera, which is a web camera installed off top of my screen. So in this loop that I'm going to create here, I'm going to read the images from this camera. First of them is the success of the reading. It's just a binary flag, and it is equal to true if the reading is performed properly. If the camera is overheated, unplugged, if it's not working, or something else is malfunctioning, this success flag will be set to false. And the second one, the second output is the frame. This is basically the image, the new image. I have to delete this one. Now we will have a frame instead of an image. Well, we don't need that anymore. We don't need to resize the image really, because the resolution of the web camera is big enough already. So I will just move some things around and delete some unnecessary parts. I will do some cleanup. Just a sec. Okay, so yeah, I will simplify the code a bit. What we're going to do here, first we're going to read the frame. Second, we're going to show it on the screen. And the last thing that we are going to do is we are going to wait for a certain amount of milliseconds, wait for a certain time. Let's wait for 30 milliseconds. Why 30? Well, that will result in theoretically something near 25-30 frame rate. It's under 1000 divided by 30 because these operations take some time as well, and this whole processing is going line by line. So one more tiny thing that we need to consider is the exiting of this loop. What can we do with that? I will skip it for now, but in just a minute we'll proceed to that. Okay, let's wait no further and run this code. Nope. I've mistaken here. It's just read, not imread. It's malfunctioning because, first of all, because the object of the camera was not released after I executed this cell, and it had some errors. The camera was not released, and the LED on top of my screen was still there. So we need to do one more extra operation. We have to first release the camera after exiting the loop. It's just for the future. And the next thing that I had to do in order to free up the camera, I had to reload the kernel. That is done by this little sign on top of the Jupyter Notebook. It's restarting the kernel. It clears up the whole context, and all the variables are deleted, and the cameras are now free. So let's start this code once again. No. That's because I have copy-pasted this code from the cell above, and we don't have any image resized here, so it has to be frame. Here, let it be frame. Again, for clarity. Okay, finally, yes. This is the view from the camera. And the nice thing here is that you're now seeing this room as it is in reality, because we are filming this near the green screen that is behind me, and this is the view from my web camera. Probably it looks a lot different to the picture that you're used to. Okay, so now we have a problem. We cannot really close this window, can we? No, we can't. So the only option to close it is to reload the kernel, but that's not a proper way to do it. And some operating systems are not really happy about it, and they will inform you that something is malfunctioning. So let us do it in the civilized manner. We can recall that function cv2.waitKey is not only waiting for a certain amount of time, but it is also returning us the value of the key that was pressed, if any. So we can extract the ASCII code of the key in the following way. First, we just take the value of the return value of waitkey function, and second, we are going to cut the last byte of it, the last 8 bits, which is in hexadecimal system 0xFF. So that's the last byte of the result of wait key, and this is the ASCII code of the key that is pressed. And now we can break the loop if the key is the one that we assigned. Okay, so we can use different options here. We can use an escape button. The escape button has an ASCII code of 27, but I prefer a different way of doing so. It doesn't require remembering the specific values of ASCII code, and we can take the ASCII code of any key here. Let's say it would be Q from quit. So if we have pressed a button Q, we can break the loop, then we will release the camera, then we will destroy all windows, and we will be done. All the program will close properly. Let's check. Indeed, it's working. Now let me do almost the same stuff, but I will change the language. So let's check if it's going to work. No, it doesn't. So if you're using any language other than English, it will not work properly. You can make this program work with non-English letters by assigning here some different ASCII codes, but the simple and straightforward way to do it is to use just English. Okay, now let us try to do the same stuff that we did to the static picture, but we can do it with a frame. Okay, so I will set some area of this frame to be bigger in the blue channel here. What do you expect? Try to imagine the picture that we are going to see now. Yep. Compare this to the one that we have got in reality. Okay, you can on your own do the same stuff with different channels. We can do it with the whole frame. Why not? Now I'm just showing in a relaxed way, so you can follow along, or you can do your own stuff. We can I'm showing different ways to access those values. So let's try to increase the values in the blue channel for all the image. Okay, let's increase it by 50 units. Here, it has become much more blue, so to say, and here you can clearly see some artifacts. So what's going on? That's because of the overflow. We have talked about the type of the data that we're using, and the type of the data is unsigned integers of 8 bits. So if we try to add too much on top of that, the value exceeds 255 and it becomes very small again. So the problem here on the t-shirt is that the blue channel is clearly overflown. We can do the same for other channels, and in such a manner we can see where the values of a certain channel are high enough. Yep. So you can get various kinds of creepy pictures with that. Try pausing the video and experimenting with those ways to change the frames. Now let us try to construct just to negate the frame, basically. So let's do it like this. We're using Python, so we're happy to use just mathematics like we do it with the numbers, but with the whole arrays, and it will work. So if you want to find out the negation of your image, you can just subtract it from 255, and that will be it. So what can we see here? We can see that the green screen is now purple screen, so the negation of the green screen is the purple screen. And my skin color is anti-light blue. And my t-shirt is now black, and in reality it's white. So it's intuitively pretty clear what's going on. And one more thing, let us just print the shapes of this frame. How big it is. Yeah, I will close the window. And the shape is the same on each turn of the loop. That's fine. So the X size of the camera is 1280, here 7020, and 3 channels as usual. So probably, almost for sure, you will have different resolution in your laptop, and that's fine. So you can try resizing the image, making it smaller, bigger, depending on do you want it to fit on your screen completely or not. So try getting used to these mathematics and these methods of working with the frames. And we are going to show, let's check a single channel here. Let's say red channel. Or no, green channel. Let's check the green channel separately. It looks like just a grayscale image, but again, that's a green channel. And if we, here we can see that this green screen is bright enough in the green channel. And if we're going to check, let's say, red channel, it will be darker. No, number 2, BGR. Yep, it's indeed darker. So try to find an object at your home with a distinct color, maybe red, green, and blue, or something like that. Maybe a combination of them, but preferably, just for the whole thing to be easier, try to find an object with a distinct red color or blue color and visualize the right channel with the methods that are given here. The next thing that we are going to do is we are going to use color space conversion. So instead of frame, I will be outputting HSV here. And you can guess which will be the color space that we're going to use. So the color space conversions, as well as all the other functions that we're going to use here, is performed with a function from OpenCV. And it is called CVT color, meaning the color conversion. So the first parameter here is the image, the input frame. And the second is a constant from OpenCV that is for convenient given by a flag. So it will be BGR2 HSV. And this function at each turn of the loop will return us the HSV representation of the frame. Let's check how does this look like. At first glance, this could look like some crazy stuff, but in reality, we can see that the shapes are clearly preserved. So this is indeed the HSV representation of the same image, okay? Nothing special. If we are going to check the channel, let's check the channel of value. Let's begin with that one. Oh, excuse me. HSV 2, yes. So the value channel is representing the brightness of the objects, and it indeed corresponds to the intuitive vision of the scene in dark or in grayscale. Yep. So that's the simplest one. And now let's move towards channel number 1. It will be the saturation channel. And what do you expect from the saturation channel? Let's compare that. Okay, so what's going on here? I think I have to visualize the original image as well, just to be able to compare them side by side. Okay, so what's going on? Why is the t-shirt black here? The t-shirt is black because it's not that much saturated. It's white, but that means that it has high values in all the channels, red, green, and blue. So let's try to find out something saturated. For instance, it's the green screen over here, and you can clearly see that it's bright enough. And regarding the transform difficulties and errors that arise during the transform from RGB to HSV, here, near the brush of the microphone, here, let's check what's going on here. So in the saturation channel, it has some high values. Why is it so? Because of the noise of the camera. And here at the region where we have lots of contrast, where we have little brushes, it's the point where the errors that arise are multiplied and increased by the color space transform. So this is the kind of artifacts that I was talking about previously. And the last one, the last channel that we're going to check is the channel number 0, which is hue. And that doesn't make much sense to us because it goes through all the rainbow from red to violet, but it is encoded here in the grayscale. So you can just tell that the hue, the color of my skin is relatively dark in the hue representation over here. And green is somewhere in between, and the darkest points here are, what are they? Yeah, this blue wall, let's say. Yeah, that makes sense because in the rainbow it's after green. So this is the HSV color space. And in the following section, we are going to talk about object detection based on color. Let us continue with the classical computer vision. So now we know how to work with the images and how to transfer them into different color spaces. Let's try to apply the pixel-wise conditions as we were talking about in the lecture. So the function that provides this functionality is the cv2.inRange function. And it's very fundamental, so we will talk about it in detail. Its input will be the mask, an image that will have the same spatial dimensions as the input and just one channel for zeros and 255s. Its input is the frame, or the HSV frame here, because we are going to apply the color-based filter in this color space. And the following two parameters will be the triplets. Those will be the lower and upper thresholds of the detection. So let us start from something simple. Let's say that all the values that are in between of 0 and 255 by all the channels, all these pixels fit our requirements. Let's try. Let's introduce a new imshow here. So let's show the mask as well. And let's omit the hue channel. Yep, this one. Okay, what do you think will happen? The mask is blank white. Why so? Because all these pixels lie in between of 0 and 255. One more thing is that I'm pressing the Q button and it doesn't result in anything for a long period of time. It is so because this processing takes some time and I'm not able to press the key in proper timing. So let's increase this time. No. The presses of Q button are sitting in the queue somewhere. So I have to reload the kernel. And now it should work properly. Yep, it's closing. Okay, so what will happen if we substitute this 0 by something different? Let's say 150. What will that give us? Okay, so maybe that's a little too much. Let's rate 100 here. Once again. No. You know what? Let's do it with the last channel. Okay, let's require 100 in the brightness channel. Yeah, great. So what do we see here? Here we have a mask of the pixels that are in HSV color space brighter than 100. The darkest spots of the original image are clearly black, and the relatively light areas are white in the mask. I hope at this point it makes sense. How does this process work and what's going on the conceptual level? So first let's increase this value. Let's say it would be 140, and what will be the difference? So with a higher threshold in value channel, less pixels in the mask are white. So less pixels from the original image meet our requirements. And if we set this value to something really big, like 210 or something, the majority of the frame will be black. And only the brightest spots will be white, like the t-shirt and some artificial lighting here, maybe my hand. Partially, yes. And if I incline it so that it reflects lots of light into the camera, it will be white in the mask. One more important thing that I have to mention is that the cameras are automatically adjusting their parameters. So this space is kind of dark, and the picture is fine. And if I would have a video call with you by Zoom, Skype, or whatever else outside, you will see the picture that will be kind of the same in terms of the color distribution and color of my skin and so on. So what's going on? That the camera has some specific software that provides the automatic adjustment for such parameters as exposure, white balance, and the post-processing of the distribution of the pixels in the image. And we can demonstrate that. So let's try to emulate the change of the lighting conditions. And now please pay attention to the mask. What's going on with the mask? Here you see. So the amount of white spots on the ceiling at the first instant when I remove my hand, it's greater than after that. Maybe I could demonstrate that with the original video. Okay, so let's suppose, yeah. Yes, that's fine. So here you can evidently see the change, the random changes of the color of the blue wall over here. So check this. The change, the shade of this blue color is changing because of the camera automatically adjusting the parameters. Obviously, the wall itself doesn't change anyhow, so that's the properties of the camera. And while we're doing robotics, we are very much concerned about the parameters of the camera that we set them to be. So if we want to participate in some kind of competition, we expect our ball or our goalposts or whatever else to be seen during the whole play. So we have to set those parameters to some specific values, and we have to turn off this automatic adjustment. And we are going to move forward. We'll talk about those parameters more in the lecture about the digital cameras. So, of course, we can detect the object by iteratively changing these 6 values, but we can also introduce a track bar here. So we'll introduce a track bar that will change the value of the lower threshold of the hue channel, of the V channel, value channel, brightness. Okay, so we'll create a track bar. And it will be lower value. It will be assigned to the mask window. And here I specify the named window, the window with the name mask. The next thing that I'm going to pass to this function is the default value of this lower threshold. The next parameter is the upper bound for this value. And the next function, the next parameter is, believe it or not, it will be a function that will do nothing. It has an input parameter 1, input parameter x, and it will do nothing with it. The reason behind such a weird set of parameters is that with the last of them, we can specify some function that will be called each time the value of the trackbar is changed. It is needed if we don't want to call a function all the time. Probably it will require some computational resources, or for some other reasons we don't want to call it all over the place. So here we just don't use this way of operating with this trackbar functionality, but it's here nevertheless. And for our example, we are going to read the value of the trackbar during each turn of the loop. So it's done by the function cv2.get trackbar pause. And here I have to specify the name of the trackbar and the name of the window. And also here I have to pass this LV instead of the numerical value that I've been passing previously. Okay, let's check. Let's check what's going on. Now the mask is purely white, nothing special. Okay, now let's try to move the threshold. Huh? Yep. So the more I increase it, the less pixels fit our requirements. And if I set it to be 255, only a tiny fraction of these pixels will fit the requirement. So what's the next logical step? The next step is to create 5 more trackbars so that we can tune this color-based filter properly using all the 6 values. So we will tune it, and then we will be capable of detecting any object really that we're interested in. Let's do that. I propose you to pause the video, try doing it yourself, and then continuing. And now I'm going to create these trackbars here. That will be a lot of copy pasting, but still, that's fine. So it will be L H S V H S V, and for the last 3 of them, it will be higher thresholds or upper thresholds. And the default value will be 255. Okay, one more thing that we need to do is we have to read the values of these thresholds. Some copy paste again. We have to do it for just a little bit more. Okay, we're pretty much done. Now let us pass these values of lower thresholds and higher values, and values of the higher thresholds. Let's run the code and see what happens. We indeed have those 6 track bars, and they are set to their default values, 0 for lower ones, and 255 for upper ones. Let's try to detect some object. For instance, let us try to detect this box on the wall, whatever it is. Let's try. I have never did that exactly for that box, so it will be an experiment. What we are going to do is we are going to move the lower thresholds up to the point when the object that we are trying to detect will start disappearing. So it has happened, and let's move the threshold backwards, like here. Okay, so now let's do the same thing for the following track bar. The point is that we are going to move it until the object starts disappearing, and then we will move it back slightly. That will allow us to specify a subspace, a cube, that will enclose the pixels of the object that we are trying to detect in the color space, in the color cylinder. Not a subcube, but let's say some just piece of this cylinder. So now we're doing this for value. Okay. Seems like that didn't help much, right? We have already used 3 of our thresholds, and the object is here. Yes, that's working, but still there are lots of other objects that have masks that do not correspond to the object that we're trying to detect. Okay, so now let us try to do the same thing, but for the upper thresholds. Let's try to limit the colors from the upper side. Here, for example, some elements of the green screen disappeared. Here's the green screen itself disappeared. Okay. So that's much better. Let's do it with the next track bar. Oh, hold on. I'm removing the object. Okay, so it seems that I cannot really detect this object using only the color-based filter, right? Its color happened to be quite similar to the color of the shades over here and the color of my hair. So we can try using some different methods to detect this specific object. And let's do one more thing. Let's move the track bars slightly backwards in order for this object to be more dense. Okay? Let's get rid of this black area over here. Yeah, that's better. Okay, so we have to use some morphology or connected components analysis, and as the result, we'll probably be able to detect this object. It's kind of difficult task, really. It's one of the most difficult objects in this frame because it's kind of small and it's dark, and there are objects that remind this one in terms of the color, but we will try to detect it. The next thing that we need to do is we have to set the default values to be like this, because I'm very lazy to tune this color-based filter again. Let's try avoiding that. So I will just copy these values, write them as the default values of the track bars. Okay, so let's check. Is it going to work or not? Yes, yes, it's working. So with this method of setting up the default values of the thresholds, you can save some time and not retune the color-based filter each time. And now let us try to think of this problem of distinguishing between all the connected components that do not correspond to the object and the one that corresponds. What's the difference between them? We could probably use morphology. We can. But the problem is that this area over here that corresponds to the human, me, this area is rather big. So we cannot really erode this area completely without eroding the area that we're trying to find as well. So probably we have to use connected components analysis. And in order to do that, let us visit the place where this connected components analysis is described even better than in documentation of OpenCV. So you have to Google it like this. How to use OpenCV's connected components with stats in Python. And it's a page on Stack Overflow, which is a good website with examples and explanations and troubleshooting. So here we're interested in the first answer over here. The beginning of this code is not that much important here. The author is just extracting a mask of a certain object, and we're interested in this part of the code. I will not rewrite it by hand. Let's skip that part. So this mask processing comes after we basically have the mask. And let us go through first the system call and second the different parts of the output. Okay, so the things that we're interested in are the first two parameters. The last one is the data type or something. It's not that much important. Let's tell you that is setting how much of the neighbors of the pixel are actually used as the neighbors in terms of the detecting if a certain pixel belongs to a connected component. So if two pixels are standing at a diagonal position to each other, they could be treated as neighbors or not neighbors. And for connectivity here means that the neighbors of the pixel are only the ones that are to the left, right, top and bottom of the pixel. And 8 connectivity will mean that each pixel has 8 neighbors. The diagonal ones are included as well. So that is not very much important in our application, but this thing is here, and you can use it if you need it. The output of this function, connected components with stats, with statistics, the output is the following. The first is the number of the different connected components plus just one for the background. The second is the image with the same size as the input with the same spatial dimensions. And the content of each pixel is the number of the connected component that the corresponding pixel of the mask belongs to. So if we have, say, 4 connected components, there will be numbers 0, 1, 2, 3, 4 in the labels mask. 0 will be for the background, and 1s will be for the first connected component, and so on. And the last thing that we are interested in is the stats or statistics. It's, well, we will print it basically, but it's the array, it's a 2-dimensional array that has, for each connected component, it has 5 values, 5 fields of top coordinate of the bounding box, left coordinate of the bounding box, width and height of the bounding box, and the area as well. It could be a little bit confusing by now, but it will become much clearer when we will use it in the loop. So we're trying to filter out the connected components that don't fit our requirements, right? So let us loop through all of them. Well, almost, right? Almost all of them. We don't have to do anything with the connected component number 0, which is the background. So we're going to loop through all of those connected components. And for each connected component, let us try to filter them by the means of area, let's say. First of all, let us have access to those values. So we can do that using the statistics array. And the first index here is the number of the connected component. And the second index here is the constant. Almost in the same way, exactly in the same way as we did it here. So basically this constant is a number, and it's specified just for convenience. So here it will be the following constant, connected component, like this, I believe, right? Stat area, okay, excuse me. Connected component, stat area, yep. First, let's just print them. Let's check. What orders of magnitude do we have here? And for simplicity, let's break the loop after just one execution of this code. Yeah. That's because I have copy-pasted the code and have to substitute this trash by mask. And the camera is hanging, so I have to reload the kernel. Okay. Yep, the code has executed, and we have broken the loop. So here we see lots of very small values, like 1, 2, 6, 12. And some of those values are in order of hundreds. And the biggest of them, this one, it's 68,000. And this is for sure the connected component that corresponds to the human in the frame. So what can we do? At least we can filter the connected components that are small. So if the area of a current connected component is smaller than, let's say, how much? 500. 500, we will remove it from the mask. And Yeah, we can actually do it like this. We can first visualize this before the filtering and then after the filtering. I think it has to work properly. Okay, so now we are going to use this label matrix, and we're going to paint it black. We're going to insert values of 0 where the label is the current label that we are considering. So mask where the label is the current label will be 0. In this way, we are going to set the values that correspond to the small connected components to 0. And now let us run the code. Okay. That makes sense. Let's import NumPy. Labels here. Okay, so what do we see here? First of all, the frames per second ratio has dropped significantly. Why so? That's so because all this connected components analysis really requires a lot of computational effort. And if we can avoid that, especially for such a big number of connected components, we have to avoid that. But if we cannot do it the other way around, well, we have to use connected components analysis. The other way to do it, let us try. Okay, let's kill the kernel. We can do it the other way around. We can create filtered mask, and it will be filled with zeros. Zeros-like, excuse me. Yeah. It will be zeros-like the original mask. So we will flip the condition. If it's greater or equal than 500, then filtered of the corresponding area, the proper area, the current connected component, we will set to be 255. And that's it. Well, yeah, that's faster. So remember that you have to keep a track of the performance, and in certain cases it could be more efficient to use in-place operations or not in-place operations. If we are trying to detect certain objects in dynamics in the process of, let's say, football game or something like that, we have to care a lot about the performance. Okay, so what do we have here? We have certain connected components that are not supposed to be here in the image still, but that's fine, we will deal with them. So there's a big one that we can delete with an extra condition over here. If the area is greater than 500 and what? And area is less than, let's say, 10,000. Oh, 1,000, excuse me. So yeah, we'll visualize only those connected components that are in the range between one and another. Okay, that's not the proper range. Seems like we have deleted the connected component that we try to detect as well. Okay, so it's somewhere on the border, right? We see that object. The question is, from which side? Seems like not from this side, right? Okay. Oh, no, indeed. So 10,000 pixels is 100 by 100. And this could be something of that order. So, wait, no, not really. Let me print the areas. Let me print the area, and then I'm going to break the loop. So now we're going to have just a couple of objects. Okay, so the problem here is that after the camera provides for a couple of first instances the frames that are not balanced properly. So there are no objects there yet. Let's separate the areas of the connected components from different turns of the loop, like this. Okay, so what do we have here? We have some smaller objects of 900 pixels, and the big one is nearly 5,000 pixels. Okay, which one are those? Okay, so let's check what's going on here in the end. I think we have to try to visualize these areas. We have to write them on top of the original frame, right? Because now I'm just guessing, I'm trying to find out if this one is the proper connected component or this one is the connected component. Let's just visualize it, right? We have our precious OpenCV functions to do that. So let's use the function put text from OpenCV to add the area on top of the connected component on the original image. So we will put this text over the frame, and the next is, let's Google that, all right? There are lots of parameters in this function. Yeah. So it's first image, then text, origin, font, scale, these things I will copy paste again. Well, not all of it, just as an example. Okay, so here I have to specify the text. This text will be really simple. It would be the string representation of the area. The origin will be, well, it has to have the same coordinates as the connected component, right? So we can do the same thing, but with the coordinates of the object. Area top, area left. It will be top and left. And we can visualize our text in that specific coordinates. So top and left. Left and top, right? I think that the x coordinate should be first. Okay, now we have to specify the font. which is this one, whatever, some default font. Font scale 1. Color, yeah, that's fine. It will be blue. Thickness 2, why not? And this is some type of line, I don't know, dashed or whatever. Let's use it with the default parameters from the example. We just have to be able to see the areas, and that's it. Okay, so let's comment that. We don't need it anymore. And here yes. The only question is what's the connected component really? So let's draw it. We have successfully drawn the areas, but let's add something else. CO2 rectangle, and that will draw us a beautiful rectangle. But in order to do that, we have to add a couple of more parameters here. So we have to extract the width and height of the object. And we are almost there, so let's draw it over the frame, and the first will be LT, the first point, the second point will be L plus width, the second point will be top plus height, then I believe it should be the color, whatever. Let's use 0 to 155, that will be a green rectangle, and 0 again. And here we have to have the thickness of the border. And I believe that's it. Yep, indeed. So judging by those variables, we can set up certain thresholds. And in order for us to detect only this object and nothing else, we can set the lower threshold to be, let's say, 4,000 or 3,050. Yes, let it be 3,050. And the high threshold will be, let's say, 6,000. Yes, that's fine. And here, let us set the thickness of the border to be slightly bigger, just for visualization purposes. Okay, that's too much. Okay, 5,000. Now I'm tuning the parameters by hand, and yes. So at the end, we almost, yes, we have this thing almost working, and yeah, at certain moments in time it exceeds 5,000. That's what's going on. Okay, let's make it bigger, right? 5,500. Okay, so now this detection is really working with certain false positives all over the place. Yes, they are somewhere here. You can see that this detection pipeline is not perfect, clearly, but it's working. And I can even incline the camera slightly, and this object still stays in place, so we can detect it. And don't judge this pipeline by the fact that it gives false positives. That's fine. The problem that we are solving is rather difficult. If you will try to perform the same detection with hat, red hat, or some green mug or something else that it has a very distinct color, it will be much easier and it will be much better. So I would ask you to do this same kind of detection but with a different object on your own, and you will have to perform really the same steps. Maybe you will have to add some morphological operations, maybe not. So wrapping this up, what had we done? We have created 6 track bars for lower and upper thresholds of the color-based filter. In the loop, we are reading the frame, getting the values of the higher and lower thresholds. We are transferring this whole image into a different color space, into HSV color space. Then we get the mask. And after that, we are filtering the connected components, the white areas in the mask, by their size. One more thing that we can do is that we can filter them by, say, the ratio between the height and the width, but that's pretty much clear. That will change only the condition here in the if statement. So please do that on your own. And that's it for today. Thanks.